Okay, again proposing the mechanism. So you see what are the changes that is taking place if you see, and then you can get the idea. You see one important point, if you see this side C double bond O and C double bond O C is, this is a ester group, this is a ketone group. The same here, no change. So if you see this part of the molecule, so this part, no change. Are you getting or not? So this part of the molecule, basically there is no change. And this part of the molecule has changed. OH is gone. So one thing I have, that is OH is gone. So OH is gone. This means what? I have to have H2O plus. I can lose H2O. Medium is acidic. So it gives me an idea, that is I have to lose H2O loss. That is a very easy thing to observe. Now you see this double bond is here. Now this double bond is here. It looks like there may be carbocation and this double bond has basically shifted. So it looks like there is a carbocation that has been formed. So carbocation is there, and then there is a shifting of double bond. Are you getting or not? So this is a shifting of double bond you have. So shifting of double bond. So this is the case. Now you see, let us try using all these ideas. So this is the molecule you have. So it's a 6-membered ring. This side OH you have. And this is same, so every time I have to write, but this molecule is not going to participate in the reaction. This is basically ester, and this side you have H plus, so I have only one option. This oxygen lone pair can attack on H plus, so this attacks on H plus, and then I will have something like this. So I will have H2O plus. If you wish, you can write H2O plus loss in this. Oh no, not a benzene ring, it's a simply cyclohexane thing. And this is you have OH2 plus. Now you have only one lone pair and there is a plus charge, and then you will have this C double bond OOCH3. This part is not participating. Now next step, what you will do, you lose H2O. So if you lose one H2O molecule, you will have something like this. So let me write here, or I can write here from here itself. So let me write, okay, let us write here itself. So you have double bond here, and then you have C double bond O, C double bond O, CH3. So this is the ester you have. Are you getting or not? And now you see this part, so basically lost, there is a positive charge. Now I have to do carbocation shift, no, hydride shift. So if I shift this hydride here, so that is a 1,2 hydride shift, I can call this as a 1,2 hydride shift. If you remember carbocation and 1,2 hydride shift. So if to shift this hydride, you will have a 6-membered ring, and there is a hydrogen now, even if there is no need to show, 2 hydrogen is there, and now this C double bond O, C double bond O CH3. Now here you have a plus charge because one hydrogen is shifted, and this carbocation is basically resonance stabilized. So this is a allylic carbocation. That's why this rearrangement or 1,2 hydride shift takes place. So this carbocation is a allylic carbocation and slightly more stable. So this double bond, and then you have a position. This position is called a allylic position. So this is a allylic carbocation, and that's why this reaction takes place, because it's a more stable. So this is a more stable. So this is more stable than 2-degree carbocation. Are you getting or not? What we will do in the next step, you just shift this double bond here. So if you shift, you will have C double bond O, OCH3. And now what I am doing is, I am shifting this double bond here, and I am writing what will happen. So you will have plus charge here, and now you see what you have to product. So you have to produce this OH here. So you can attack H2O molecule in the next step. So attack of H2O. So this is acting as a nucleophile. This is a neutral nucleophile. Everybody knows. Now at the same point of time, you will have oxygen. There is a plus charge. So you can lose H plus from here, and then you will get the final product. So easy. So you have this double bond O and double bond OOCH. This ester and ketone remains as it is, And now if you lose H2O, so this is basically keto form and enol form tautomerization. So this is enol form of the same molecule. So this is a enol form. And this will go into tautomeric mixture. So in solution it will exist in tautomeric mixture. You will have a keto form of the same compound. So let me rub here. So things are becoming slightly difficult. So let us say, if I rub this part, now you can see. So you will have oxygen and CH3. And there is a double bond. Oh, you see this is a keto-enol tautomer, so this goes here, this goes here. So you will have a double bond O. So in this case you have enol form and this is your keto form. So they exist in tautomeric mixture. Are you getting or not? So but we have to prove this enol form only. So you have to write mechanism for enol form. So this up to here you can write. So this is a enol form. Are you getting? So easy.